All right, today we're going to be taking a look at rational exponents and radical expressions. And so before we dive too much into this, it's a good idea to go over the vocab, what these two words mean. So a rational exponent is a fractional exponent, and it can be written as a radical expression, which we'll get into in just a moment. But what I mean by a fractional exponent is that we actually have, like x to the 2/3 power, where the exponent is actually a fraction. And so these rational exponents, they can actually be written as radical expressions, which include square, cube, fourth, roots. So a radical expression, you might have seen these before, include like the square root of x. We could have like the cubed root of y, and we can have other complex radical expressions. But rational exponents can be written as radical expressions, and radicals can actually be written as irrational exponents as well. So we're going to learn how to do that. So looking at, this is a root right here, and this is the square root symbol right here. And we're going to talk about what these different numbers and variables mean. So first of all, this small number right here is called the index. And this is actually a really important number because when we're simplifying radicals or transferring from radicals to rational exponents, this tells us that we're making groups of this amount. So whatever that number happens to be, we're making groups of that amount. This number right here, we're familiar with exponents, is an exponent. And then this, whatever is under the radical symbol, is a special name. It's called a radicand. So if we were to rewrite this radical expression as a rational exponent, how we would write it is we would keep our base, b, and then we would raise it to the m over n. So the exponent would go on top, and the index, or the root, would go on the bottom. And so if we look over here, this is just another way of looking at it, but where we would have b to the m over n. But the reason that this one is important, because if we notice the parentheses on this version, those parentheses are really important when we see things like this. So if I had the nth root of ab raised to the m, this is quite important because what this means is that everything under this root, the a and the b, are being raised to the m over n. So I would want to rewrite this with parentheses, ab to the m over n. If I just wrote ab to the m over n like this, it would imply that only the b is being raised to that power. So we don't want to do that. We want to use parentheses to show that actually a and b, the entire quantity, is being raised to the m over n. So as we're working with radical expressions and rational exponents, it's important for us, especially when we get into simplifying, to be able to know offhand our perfect squares and perfect cubes. So we can just kind of fill in this chart and use it as a reference as we work through simplifying some of these radical expressions. So here we have 1 squared, which what that means is we have 1 times 1. So 1 times 1 is 1, and so that means that the square root of 1 is 1. We have 2 squared, which means 2 times 2, that equals 4, so the square root of 4 is 2. 3 squared is 3 times 3, that equals 9, so the square root of 9 is 3. 4 squared is 4 times 4, that equals 16, so the square root of 16 is 4. 5 squared, that's 5 times 5, equals 25, so the square root of 25 is 5. 6 squared is 6 times 6, it equals 36, so the square root of 36 is 6. 7 squared, that's 7 times 7, it equals 49, so the square root of 49 is 7. 8 squared is 8 times 8, which equals 64, so the square root of 64 is 8. 9 squared is 9 times 9, which equals 81, so the square root of 81 is 9. And 10 squared, that's 10 times 10, is 100, so the square root of 100 is 10. And so these are really helpful as we are solving and simplifying radical expressions. And it's also helpful to be familiar with perfect cubes, because sometimes we won't be taking the square root, but we may be taking the cube root of a expression. And so in the same way, we want to be familiar with these. So it's the same idea, but if I have 1 cubed, that's 1 times 1 times 1, which still equals 1. So the cubed root of 1 is 1. 2 cubed is 2, sorry, that's a 3. That gives me 2 times 2 times 2, which equals 8. So the cubed root of 8 is 2. 3 cubed, that's 3 times 3 times 3, which equals 27. So the cubed root of 27 is 3. 4 cubed, that's 4 times 4 times 4. It equals 64. So the cubed root of 64 is 4. 5 to the third power, 5 cubed is 5 times 5 times 5, which equals 125. So the cubed root of 125 is 5. 6 cubed is 6 times 6 times 6, which equals 216. So the cubed root of 216 is 6. 7 cubed is 7 times 7 times 7, which equals 343. So the cubed root of 343 is 7. 8 cubed is 8 times 8 times 8, which equals 512. So the cubed root of 512 is 8. 9 cubed is 9 times 9 times 9, which equals 729. So the cubed root of 729 is 9. And then 10 cubed is 10 times 10 times 10, which equals 1,000. So the cubed root of 1,000 is 10. So you can refer back to this as we begin simplifying, but these are just helpful things to know, and I think the more that we work with simplifying radicals, the more that these will become familiar to you as you use them frequently. So the final thing that we kind of want to look at, and that is also very helpful to know, is the divisibility rule. So if we have a number that's not a perfect square or perfect cube, we want to start somewhere by factoring it down when we're simplifying radicals. So it's very helpful to know divisibility rules. So these are things we can just know off the top of our head to know if a number is divisible by another number. So the first one is to know if a number is divisible by 2. You can check if the last digit is even, meaning it ends in a number like 0, 2, 4, 6, or 8. So we know that if a number does end in one of these numbers, then it is divisible by 2. So in this example, 3,978 ends in 8, which is even, so yes, it's divisible by 2. However, this number, 4,975, ends in 5, which is odd, so this number would not be divisible by 2. If we look at the divisibility rule for 3s, what this means is a number is divisible by 3 if the sum of the digits is divisible by 3. So that means if I add up all these numbers, like 3 plus 1 plus 5, that gives me 9. Well, 9 is divisible by 3, so that means that 315 is also divisible by 3. This example, however, 139, if I add these digits together, I get 13. 13 is not divisible by 3, so this number is also not divisible by 3. The next example is divisibility by 4. So if the last 2 digits form a number divisible by 4, that means that it's divisible by 4. So if we look at these last 2 digits, 12 is divisible by 4, so that means that this entire number is divisible by 4. And 7,518, 18 is not divisible by 4, so this number is not divisible by 4. The next one is divisibility by 5. So we know numbers are divisible by 5 if the last digit is 0 or 5. So in 14,975, it ends in a 5, so yes, it's divisible by 5. 10,978 does not end in a 0 or 5, so it cannot be evenly divided by 0 or by 5. The next one is 6s. So we know a number is divisible by 6 if the number is divisible by both 2 and 3. So we have to look up at those rules. We know it's divisible by 2 if it's even, and 3 if the sum of the digits is divisible by 3. So 48, it's even, so yes, it's divisible by 2. If I find the sum of the digits, 4 plus 8, that gives me 12. 12 is divisible by 3, so it's divisible by 2 and 3, so yes, it's divisible by 6. The number 20 is even, so it's divisible by 2, but if I add the digits, 2 plus 0, I get 2, which is not divisible by 3, so it can't be divided by 6. We're going to skip sevens because the rule for divisibility for sevens is so complicated. It's just not easy to remember or to use, and so it's better just to, if you're curious about sevens, just plug it in your calculator. The same kind of applies for eights. The rule for this is a little bit complex, and so usually I would just kind of plug it in my calculator. But you can know if a number is divisible by 8 if the last 3 digits form a number divisible by 8. So what that means is if we look at these last 3 digits and we know that that's divisible by 8, we can know that the entire number is. But I don't know about you, but I'm not very strong in my 3-digit divisibility, so I wouldn't necessarily know just by looking at 664 if it is or is not. And so I would probably just plug this entire number in my calculator to see if it's divisible by 8 or not. But you may be pretty familiar, and this may be helpful to you in some cases. But in this case, 664 is divisible by 4, but divisible by 8, but 212 is not. If we look at 9s, this rule is very similar to 3s. We know a number is divisible by 9 if the sum of the digits is divisible by 9. So if we add all this together, I get 7, 8, 9. The sum is 9, which is divisible by 9. And 93, if I add that together, I get 12. 12 is not divisible by 9, so 93 is not divisible by 9. And finally, 10s, this one's pretty straightforward. We know a number is divisible by 10 if the last digit is 0. So 15,990 ends in 0, so it can be divided by 10. 10,536 does not end in 0, so it cannot be divided by 10. So those are just some really good things to know and keep in mind as we move forward. So now we're going to work through some examples of rewriting these expressions and also simplifying. So if you flip to the next page of your guided notes, we're going to work through this table together, and we're going to practice using some of these rules and also simplifying the radical expressions. So what we have over here is showing us an example of the rule, and then we're going to transfer a radical expression into a rational exponent, and then we can simplify it. So this radical expression, it tells us the square root of b equals b to the 1 over 2. The reason we get 1 over 2 is because if we have no exponent, it's assumed that it's a 1, and if we have no root, it's assumed that it's a 2. So we put exponent on top, root on bottom. That's how we get b to the 1 over 2. So in the same way, if I have the square root of 49, there's a secret 1 here and a secret 2 here. So this could be written as 49 to the 1/2 power. Now, to simplify this, what we're going to do is we're going to use the index to figure out how many, what kind of groups we're making. Since the index here is 2, it means we're looking for groups of 2. So when I split 49 down into its factors, I'm looking for pairs of numbers. Well, I just happen to know that 49 is a perfect square, and it splits into 7 and 7, which means 7 times 7 equals 49. And 7 and 7 are the same number, so I make a pair, and then I can take out the 7. And so I know that the square root of 49 is 7. So that might seem like a lot of work for a number that you already know is a perfect square, but you'll see that this process can be helpful as we work with larger numbers and more complex examples. So the next one, we're taking the cubed root of b, which equals b to the 1/3. Once again, 1 on top because there's a little 1 here that's invisible. And so when we take the cubed root of 64, we can rewrite that as, if we have a little 1 here, 64, it's not wanting to write, 64 to the 1/3 power. And so if I were to simplify that, what I'm looking for this time is groups of 3. So when I split 64 down, I'm going to look for groups of 3 inside 64. Now, we just filled out our list of perfect squares and perfect cubes, so if you know off the top of your head that 64 is a perfect cube, you could go ahead and split it into those 3 groups now. But I'm going to go ahead and factor this down if you didn't happen to know that information. So 64 I know is a perfect square. I know it's divisible by 8 and 8. But I'm looking for groups of 3 and I don't have one. So I need to continue factoring. I know 8 factors into 4 and 2, and this 8 can factor into 4 and 2. But I still don't have groups of 3. So if I continue factoring, I can factor this 4 into 2 and 2, and this 4 into 2 and 2. Now I should be able to make groups of 3. I have 1, 2, 3 over here, 3 2s, and then I have 1, 2, 3 2s. So what I can do, I can take out a group of 2s and another group of 2s, and I multiply those together to get 4. All right, moving on to the next one, we have the 4th root of b, which equals b to the 1 over 4. Again, we get the 1 on top because there's a secret 1 here when there is no exponent. So the 4th root of 81 can be rewritten as 81 to the 1 over 4. Now to simplify this one, we are looking for groups of 4. I know that 81 is a perfect square, so I'm going to go ahead and split it down into 9 and 9, meaning 9 times 9 equals 81. I still don't have groups of 4, so I'm going to factor each of the 9s down. 9s factor into 3 and 3. So now you can see that I do have a group of 4. 1, 2, 3, 4, 3s, so I take out a 3. The next example is the square root, remember there's no number here, it's a square root, of b to the 3rd power. So this can be rewritten as b to the 3 over 2. So if I have the square root of 9 to the 3rd power, this can be rewritten as 9 to the 3 over 2. If we're simplifying, we want to remember there's a 2 here and that we're looking for groups of 2. But what I have is 9 cubed on the inside. So that means I have 3 9s. So 9 times 9 times 9. Then I'm looking for groups of 2. Well, I already have a group of 2. 9 times 9 is one group of 2, so I can go ahead and take out a 9. But this 9 needs to be further factored into 3 times 3. So now that I have another group of 2, I can take that out as well. I multiply them together, and 9 times 3 gives me 27. The next example is the cubed root of b squared, which equals b to the 2 over 3. So here I have the cubed root of 64 squared, which can be rewritten as 64 to the 2 over 3. So what 64 squared means is that I have 64 times 64. And this time I'm looking for groups of 3. I only have 2 64s right now, so I need to continue factoring. 64 is a perfect square that factors into 8 and 8, and this 64 also factors to 8 and 8. So you may see already that I have a group of 3. I have 1, 2, 3, 8, so I can go ahead and take out an 8. However, I'm still not finished. This 8 needs to be further factored into 4 and 2, and then this 4 into 2 and 2 until I have a group of 3 2s that can also be taken out, and I multiply that by 8 to get 16. All right, this final example is, if we look at the example, we have the 4th root of b to the 3rd, which can be rewritten as b to the 3/4. So if I have the 4th root of 16 to the 3rd, this can be rewritten as 16 to the 3 over 4. And so what I'm looking for is groups of 4, but I have 16 cubed, which means I already have 3 16s. However, I still don't have groups of 4, so I need to continue factoring. Each 16 can be split into 4s. 4 times 4, 4 times 4, and 4 times 4. So at this point, I should be able to make at least one group of 4. So 1, 2, 3, 4. So I'm going to take out a 4. But I need to continue factoring the 4s over here. Each 4 can factor into 2 and 2. So I have 4 2s, and I can also take out a 2. So 4 times 2 equals 8. So that is how we simplify radical expressions and how we can switch between radical expressions and rational exponents.